this video, we're going to apply some of the things that we learned concerning the conformations of alkanes to the conformations of cycloalkanes. And perhaps the best place to start is with a diagram that we'll have seen in class. So here we have a number of ring structures, all the way from cyclopropane to cyclohexane. And our focus will actually be on the first three, the cyclopropane, the cyclobutane, and the cyclopentane. At least that would be the focus in this video. Now, if all of these ring structures were planar, then we would expect bond angles of 60 degrees, 90 degrees, and 108 degrees. As it turns out, the experimental bond angles, or the actual bond angles, at least for the middle two, the cyclobutane and the cyclopentane, do not agree with the structure being planar. And it's helpful to investigate why that's the case. A good place to start would be to revisit some of the definitions concerning the various strains that can exist. So you are already familiar with the idea of torsional strain and steric strain. Torsional strain, of course, is the repulsion of bonding electrons of one substituent as they pass close to the bonding electrons of another substituent. We talk about whether or not bonds are staggered or eclipsed, and of course, when the bonds are eclipsed, we have substantial torsional strain. Steric strain is a strain experienced by a molecule when atoms that are not directly bonded to one another are close enough that their electron clouds interpenetrate. Now, when we're dealing with rings, we tend not to talk about steric strain as much unless we're talking about substituents that are on the ring. So in this video, we will not mention much about steric strain. We will, however, talk about angle strain. So of course, angle strain is a strain experienced by a molecule as a result of its bond angles being distorted. And a good example of when bond angles will be distorted is when we have a ring structure. And what we mean by distorted is when the bond angles are not ideal for sp3 hybridized carbons. And of course, the ideal bond angle would be 109.5. It's helpful to look at cyclopropane. So of course, cyclopropane exists of only 3 carbon atoms. And the bond angles that would exist in this ring structure is 60 degrees. Of course, that's way off from 109.5. Now, if we look at the structure right up here, where we have, for instance, just a chain of carbon atoms, the carbons are adopting a tetrahedral orientation, and the sp3 hybrid orbital of one carbon can overlap very well with the sp3 hybrid orbital of another carbon. And this very good overlap results in strong sigma bonds. Over here, which is a representation of cyclopropane, because of the 60-degree bond angle, it's not possible for the sp3 hybrid orbital to overlap well with the sp3 hybrid orbital of another carbon. This is what we call angle strain. As you might imagine, the molecule of cyclopropane is highly reactive because these bonds are relatively weak. Now, cyclopropane also suffers from another problem. If we were to look down any one of these carbon-carbon bonds, so we can look down from here to here, or what I'm going to show you is I'm going to pretend this is an eyeball, although it looks like a Pac-Man, and I'm going to look down from carbon here to carbon here. And as such, looking down these carbons, we would see that the carbon-hydrogen bonds are eclipsed with the carbon-hydrogen bonds behind them. And in fact, all the bonds are eclipsed, and you'd see a Newman projection that looks something like on the right here. So not only does cyclopropane suffer from severe angle strain, it also suffers from torsional strain. And I highlight that here. The angle strain is high, and the torsional strain is high. It's helpful to look at the cyclopropane also using in simulation software. If we start off by looking at the cyclopropane, it's pretty easy from this diagram to see that the bond angles here are indeed 60 degrees. And if I turn it on its side, it's pretty easy to see, looking down any one of these carbon-carbon bonds, that we have significant torsional strain. And so this is a highly unstable molecule due to both the angle and the torsional strain. Okay, so let's continue now and take a look at the cyclobutane. Now, cyclobutane, if planar, would have bond angle of 90 degrees, which of course is not good either. However, what seems to happen with cyclobutane is that experimentally it adopts what we call a puckered structure, or indicated here, a butterfly structure. The bond angles here are 88, so that's even worse. So there has to be a good reason for why that happens. As you might imagine, it has to do with torsional strain. So if you look down any one of these carbon-carbon bonds, you'll see that the hydrogens are eclipsed. There is significant torsional strain. However, when the cyclobutane adopts this butterfly structure, and if you look down, for instance, and I'm showing you my Pac-Man or eyeball again, if you look down from this carbon to this carbon, you would see that the carbon-hydrogen bonds are now slightly staggered, if you will, or at least there's reduced torsional strain. So it's not perfectly staggered, but it is an improvement. And in fact, it would be rather amazing if you could actually witness these molecules in space, for instance, because they would interconvert between two different conformers, and it would look like the molecule is actually flying like a butterfly. So it would be the pucker up and then pucker down, pucker up, pucker down, of course moving at billions of times per second. So one of the things that we can do in terms of representing what's going on here is we can say moving from planar to butterfly, the angle strain does indeed increase and remains relatively high. The torsional strain, however, decreases to something that's moderate. At least we have some staggeredness to the conformation. So again, let's take a look at a simulation. Okay, so here we have cyclobutane, and looking down through this hole, it might look like, in fact, it's adopting a conformer with 90 degrees. But if we take a closer look, I'm going to approach it a little more closely and then turn it on its side, we indeed see that it adopts this butterfly structure. If you look down any one of the carbons, you can see that the carbon-hydrogen bonds on adjacent carbons are somewhat staggered. It's not a perfect staggering, but it's definitely better than having a completely eclipsed structure. So remember that this conformer fluctuates with another conformer, so it would look indeed a little bit like the flapping of a butterfly. So remember, the bond angles here are, instead of 90 degrees, about 88 degrees, but there's a reduction in torsional strain. Okay, so now we're back to look at the last example, and the last example in this video will be the cyclopentane. So the bond angles in this planar structure are actually quite ideal, 108. So that's very close to 109.5. The problem, of course, in this planar structure is, once again, 10 carbon-hydrogen bonds are totally eclipsed. And so there's significant torsional strain. As it turns out, the experimental structure for cyclopentane is this sort of envelope structure. And if we look down, for instance, and I'm going to show you my Pac-Man again, looking down from this carbon to this carbon, we would see a Newman projection that looks something like this down here, where the carbon-hydrogen bonds are even more staggered. And in fact, it's quite close to ideal staggeredness. And so adopting the envelope structure is quite beneficial in terms of reducing torsional strain. Now, that's not true about looking down all the carbon-carbon bonds and comparing where the carbon hydrogens are. So for instance, if we look down from this bond to this bond in this particular envelope structure or envelope conformer, these bonds would still essentially be eclipsed. However, similar to our butterfly structure, which is constantly in motion, this envelope structure, in a sense, has 10 different conformers that it can interconvert. And so there's sort of spreading out the staggeredness. And so we can summarize the notes here by saying that moving from planar to envelope, we have an angle strain that increases, but still somewhat moderate. 104 degrees is not that far from 109.5. The torsional strain, however, decreases from something that's quite significant to something that's relatively low. So this is why it adopts these envelope structures. So I would like you to be able to recognize this, but also be able to justify why this is the case. Again, it's helpful to look at the simulation. And so let's take a look at that. So here we have cyclopentane. I'm going to approach it a little bit more closely. Of course, looking from the top here, it does look like it's a planar structure, but now as we turn it over, we indeed see that it adopts this envelope structure. Now, certain carbon-carbon bonds are indeed quite staggered, if you will. And so I'm just going to move this a little bit so that we can see the envelope. So let me just move it around a little bit more. There. So you can kind of see the envelope where this portion here is raised. And certainly if I look down, for instance, from this carbon to the carbon back, the structure looks somewhat eclipsed. However, if we look from this carbon down to this carbon, we can see clearly the carbon-hydrogen bonds on adjacent carbons are more staggered. And so overall, this envelope structure has less torsional strain compared to the planar structure. Of course, this is at a sacrifice of bond angle. So we go from a bond angle of 108 degrees down to 104 degrees. And so in this video, we've reviewed why cyclopropane, cyclobutane, and cyclopentane adopt the structures that they do, what the problems are in terms of torsional strain and angle strain, and how for cyclobutane and cyclopentane it's advantageous to adopt a puckered or a butterfly shape or an envelope shape to, in a sense, reduce the torsional strain at the expense of some angle strain. In class, we'll spend considerable amount of time looking at cyclohexane, as there's a number of different things that we need to be able to do concerning this most popular form of ring structure.